If you were to look very closely at the reed of a clarinet, for example, as someone was playing it, you would see the reed going up, down, up, down. Now, of course, in real life, this vibration would be very fast, but there's still that motion, and that's that motion that creates the first vibrations, which then allow the clarinet to make a musical sound. Similarly, if I have this bottle and I blow over it just the right way, it makes a musical sound as well. Once again, air is rushing along over the hole, and it's creating the first vibrations, which then set up the standing wave in the bottle itself. But how exactly does blowing air over the opening of this bottle create these first vibrations? And how exactly does blowing over the top of a reed make it vibrate? Well, to get an idea of how blowing across things make them vibrate, we're going to look at an idea in physics called Bernoulli's principle. So the idea behind Bernoulli's principle can best be described by thinking of air flowing through a tube. So you blow in air through this side of the tube, and it exits out this side. But as you can see, this particular tube changes its diameter, becoming narrower right here. Now the same amount of air going in at the left must be coming out at the right every second. So if the tube gets narrower, the flow of air must speed up in the narrower part. This is exactly what happens when to water in a river, for example. When the river narrows, the flow of water speeds up, and we call that the rapids. And then if the river gets wider again, that same water flow slows down. And what Bernoulli realized is that if the water speeds up, going from left to right here, then it must have accelerated. But as we know from Newton's laws, acceleration requires a net force pushing in the direction of the acceleration. So we need a force which pushes to the right in this area. So where does this force come from? What is providing the forward force to the right, which speeds up this air? Well, I don't think you're going to be able to guess it, actually. If I were to guess, my first thought would be that the force comes from the walls of the tube here where it's closing. After all, if I want to shoot water at the end of the hose, I press my thumb over the end of the hose, and that pressure causes the water to shoot out faster. Unfortunately, this can't be correct since the forces from the walls press either inward or backward. They can't accelerate this air in the right direction. So therefore, Bernoulli correctly reasoned that there must be an internal force which is higher in the wide, slow part of the tube, we'll draw an H here, and less in the narrow, fast part of the tube. We draw an L for low pressure here. That internal force is what we call pressure. And this is Bernoulli's principle. When the speed of airflow increases, it is accompanied by a reduction in the internal pressure of the air. Conversely, if the flow slows down, the pressure will increase. Okay, so Bernoulli's principle tells us that air that's in a narrowing tube that's speeding up has a decrease in internal pressure. And conversely, if the tube is getting wider and the airflow rate is slowing down, the pressure will increase. But now let's return to this bottle. How does Bernoulli's principle relate to this, and how does it set up vibrations in the air in the bottle? Well, let's draw the bottle, and let's assume that our lips are here, and we've narrowed the flow of some air so that this fast airflow has reduced pressure compared to the air inside the bottle. So we can draw a little H for high pressure inside the bottle and L for low pressure outside the top. And what happens next is that the pressure difference causes the air to be pushed out of the bottle and join the flow of moving air. But this flow of air out of the bottle has its own inertia, which causes it to overshoot equilibrium. So as it flows, it empties the bottle a bit, reducing the pressure in the bottle until the pressure difference is reversed. So we can draw this again and draw the new situation as H outside the top and L inside the bottle. And remember, we talked about this overshooting equilibrium back in the oscillations chapter. We talked about it in terms of a swinging pendulum, for example. As it goes through equilibrium, it wants to go beyond and then come back. So this is exactly the same reasoning here. So this reversed pressure difference, what it does is it causes the airflow to reverse and start flowing back into the bottle from that moving air column. So again, this flow overshoots equilibrium, so that, we'll draw it again, the pressure now is higher in the bottle than above the bottle. So we end up right back where we started with the H inside and the L outside, and therefore we have set up an oscillating pressure at the top of the bottle. So these are the first vibrations which in turn set up the standing wave inside the bottle. The bottle is acting as a column of air which is closed at the bottom and open at the top, and this can support standing waves of certain frequencies as we've seen in previous chapters. So that's how Bernoulli's principle helps drive first vibrations in non-reed instruments such as the flute. You can use a similar explanation to describe how air rushing over the top of the reed in a clarinet, like this one, can produce the same kind of effect. And I can sort of show you the basic idea using this ruler. I'm going to blow over top, and what that's going to do is that it's going to reduce the pressure over the top of the ruler, which is going to cause it to start coming up. And as it comes up, it overshoots equilibrium until it's actually compressing the air against the mouthpiece of the clarinet, and then that's going to reverse the motion of the ruler. It'll then overshoot equilibrium again until that moving airflow sucks it back up, and then you get that vibration. Okay, so the steady airflow gives it the input power, and then it's the elasticity of the reed which gets it vibrating. And we can try to do it in real life